6.1, the polygon angle sum theorems. We are moving on from triangles to polygons, and specifically in chapter 6 we deal a lot with quadrilaterals, but we are going to learn some basic polygon theorems here. And 6.1 starts us out. Our objective is to find the sum of the measures of the interior angles of a polygon. That should sound very familiar, our triangle angle sum theorem. I promised you that we would get one that was for polygons, for all polygons, and to find the sum of the measures of the exterior angles of a polygon. Do you remember what the sum of the exterior angles of any polygon is? We'll see if you do. Now, remember when I told you that all figures are made up of triangles? Well, what we're going to find out is that the sum of the interior angle measures of a polygon depends on the number of sides and basically the number of triangles. And we are going to show that they are all some multiple of 180 degrees. And of course that's true because it's our triangles. Another thing to remember here is that in this textbook, a polygon is convex unless otherwise stated. That means it doesn't have any inside angles. A concave polygon would look something like that. So no, none of those. All of them have outward pointing angles. Some information up here are our prefixes that tell us how many sides. You know, triangle and quadrilateral, pentagon, hexagon. You might not know 7. 7 and 9 are probably the only ones you're not familiar with. So if you don't know what it is, you could say it's either 7 or 9. 7 is hepta or septa, and 9 is nona, non. And of course, octo and 10 is deca. So those are our prefixes for our polygons. Let's take a look at our first theorem here. The first theorem is the polygon angle sum theorem. It's not quite as fun as our triangle angle sum theorem, but it's a good one. It says the sum of the measures of the interior angles, we should know in measures, of an n-gon, and n is just the number of sides. So we can have a 20-gon or a 1,000-gon or a 469,287-gon. The sum of the measures of the interior angles of an n-gon is the number of sides minus 2, that quantity, times 180. So we are going to box this. That is our formula that we are going to use. And let's take a look at why this is true. Let's first take a look at our triangle. How many sides does a triangle have? Triangle has 3 sides. So what's 3 minus 2 is just 1 times 180. So a triangle is 180 degrees. We know that, triangle angle sum theorem. What about a square or a quadrilateral? Doesn't have to be a square. N is 4. So what's 4 minus 2? 2. So that's 2 times 180. So that's 360 degrees. We know that. How do we know that? Because a square is 2 triangles. What about a pentagon? What's n on a pentagon? N is 5. What's 5 minus 2? 3. 3 times 180? It's 540 degrees. And let's do one more. Let's do hexagon. Another color here. Hexagon. N is what? N is 6. What's 6 minus 2? 4. 4 times 180? 720 degrees. a little better hexagon there. And we can go on and on. As a matter of fact, we can look at our first example here. It says, what is the sum of the interior angle measures of a heptagon? Well, we know hepta means 7, so this is n equals 7, and you should always make a little note of that. These are our, define, explore stuff. What do we know? So we write our formula here. The sum of the measures of the interior angles of a heptagon is n minus 2 times 180, 7 minus 2, 5 times 180 is 900. So that's 900 degrees, and we can say sum of the interior angles of a heptagon, we can put a little 7 down there, 900 degrees. Just like all of these others, that's always going to be true. So you now know everything for triangles, quadrilaterals, pentagons, hexagons, and heptagons, and you could easily find them out for a nonagon and a decagon if you'd like. All right, it looks like it is your turn here. Go ahead and pause the video and do the next couple of problems. All right, that first one was pretty easy. The sum of the interior angle measures of a 17gon. Well, all we have to do, we know that n is 17. We use our formula, 15 times 180, 2,700 degrees. That's a lot of degrees. There's a lot of sides. The second part here, if you label what you know, write your formula, and substitute in, that's all math is, then this one was pretty easy. It says the sum of the interior angle measures is 1980 degrees. How can you find the number of sides? So we wanted to find the number of sides. So I simply wrote my formula. The sum of the interior angles is quantity n minus 2 times 180. Well, this time, instead of knowing n, we know the sum. So I just put in 1980 there, divide both sides by 180 degrees, and this cancels. And I get 11 equals n minus 2. I add 2 to both sides. N is 13, so we end up with a 13gon. Well, those were fun. Okay? Some more vocabulary for us here. An equilateral polygon. What does equilateral mean? Equal sides. So that is just a polygon with all sides congruent. There's our picture. An equiangular polygon. What's equiangular mean? Equal angles. So equal angles, equal sides. Equiangular polygon is a polygon with all angles congruent. And there we go. Now, hopefully you can see that both of these things are very good for us and would make life a lot easier. And if we have all of that, life is really good. This is called a regular polygon. And yes, I'm putting it in red. You are actively looking for regular polygons. A regular polygon is a polygon that is both equilateral and equiangular. And yes, good things happen when we have regular polygons. Now let's go back up for a minute. Our polygon angle sum theorem is true for all polygons. Doesn't matter if you're equilateral, equiangular, regular. Some of these things that we're going to learn are true only for regular polygons. And that's our next theorem here, the corollary to the polygon angle sum theorem. What does corollary mean? Corollary means an extension or a special case, and in this special case is a regular polygon only. So our corollary to the polygon angle sum theorem says the measure of each individual interior angle of a regular n-gon is this formula right here, the quantity of n minus 2 times 180 all divided by n. And this should make perfect sense for you. This is the total, the sum of the interior angles. Let's write that because that's really, this is the sum of our interior angles divided by the number of sides, which is also the number of angles. So this should make perfect sense. Let's look at our example here. It says the common house fly has eyes that have 4,000 facets. None of that's important to us. Each facet is a regular hexagon. That is important to us. Hexagon means we know that n equals 6. So what is the measure of each interior angle in one hexagon facet? All right, so we simply write our formula. The measure of one of the angles in our regular hexagon here, and we know that n is 6. We substitute in. We get 4 times 180 divided by 6. We end up with the measure of one interior angle of our hexagon, or you can write hexagon. Sometimes I do that. Is 120 degrees. So in our hexagon here, this is a regular hexagon, we can mark all of these congruent, and they're all 120 degrees. All right, I'm guessing that that is your cue, yep, to pause the video and try the problem. That was a fun problem. We wanted to find the measure of each interior angle of a regular nonagon. We know that non is 9, so we simply write out our formula, and we know 9 minus 2 is 7 times 180 divided by 9, and we get the measure of each interior angle of a nonagon is 140 degrees. So this should make sense to you. This should seem, you should go, yeah, that's probably, correct, because the more sides you put in, the bigger your angles are getting. If we have, we'll call this a regular triangle, so an equilateral triangle, what was our interior angle measures? Those were all 60 degrees, right? 180 divided by 3 is 60. And then if we do a regular quadrilateral, which is just a square, what are all of these? These are all 90. 360 divided by 4 is 90 degrees. Look at, they're starting to get bigger. And we could do 5. We just did 6. 6 was 120 degrees. 9 is 140 degrees. Okay, so you can see that these are starting to get larger. The more sides you add, the wider your angle gets. Now, we are never going to go above 180 because that would be a straight line. So it goes up quickly at the beginning, right? 60 to 90 is a big jump. But look, from 6 to 9, we went 120 to 140. So the more sides you add, the angles are going to get bigger, but it's at a slower pace because we're getting closer and closer to becoming a circle. All right, let's look at our example here. Oh, we should go back to our polygon angle sum theorem. So we have a figure over here, and we want to know what is the measure of angle y. So I am looking for the measure of angle y. in the pentagon today, we could even just count up the sides. We know that n equals 5. So for our pentagon, when n equals 5, we need to know the sum of all of the angles. We know that the sum of the interior angles of a pentagon is what? We did this one on the front. It's 540 degrees. So then what are we going to do? Well, we're just going to take, we know that's a 90 degrees, nice little right angle there. We know if we add all of these up, subtract it from 540, measure of angle y, turns out to be 70 degrees. Nothing new here. We've done this on triangles for a long time. It's just now, if you notice in the problem here, they set it up, here is our sum of our angles. I would find the sum first, kind of separately, and then put it all together. I just find that to be easier. You might as well. So go ahead and it's your turn to do the next problem. We were asked to find the measure of angle G in quadrilateral EFGH. So quadrilateral, or you just count up the sides, we know that n equals 4. So I know the sum of the interior angles of a quadrilateral is 360. If I don't know that, I can find it using our Polygon angle sum theorem. And then I just add up all my interior angles, set them equal to 360, and I find out that the measure of angle G is 102 degrees. So slightly more work than our triangles, but not by much. Okay, so that's our interior angles. We were promised some exterior angles, and here they are. And we have drawn exterior angles before. You know that an exterior angle is made up of a side and the extension of another side. So we just draw the line, and we found out on triangles that all of those added up to, what was it? 360 degrees. You remember that? If we do it for our quadrilateral here, we extend our sides and we fill in our exterior angles, simply a linear pair, right? This right here is just 180 degrees. This right here is just 180 degrees. We can find our exterior angles, we add them all up, 360 degrees it is. So this brings us to, we can almost fit everybody on there. This brings us to our last theorem, and this last theorem is true for all polygons. And it says the sum of the measures of the exterior angles of a polygon, one at each vertex, is 360 degrees. This is true for all polygons. So if we are looking at our pentagon here, we extend our sides, and remember I told you that I like to extend them in a pinwheel pattern because it makes it easier to see the exterior angles. Make sure you have all of them. Those are always going to add up to 360 degrees, no matter whether you have a triangle, a pentagon, a octagon, nonagon, 17gon, 120 million gon. Always 360 degrees. Now, this next example here is not a theorem, not a corollary, but it's really important to us, and this is going to be for regular polygons only. We want to find the measure of angle 1 in a regular octagon. Well, what do we know? we know that all of those add up to 360. So how are we going to find one of them? Well, we take 360 and we divide it by how many angles there are. And it just so happens the number of angles is the same as the number of sides. So if you look here, the measure of angle 1 is 360 divided by the other 8 angles. And what we know is that all of these angles, these exterior angles, are congruent because it is a regular polygon. Regular polygons, all angles are congruent. That's interior and exterior. Because if your interior angles are congruent, so are your exterior angles. So we have a formula that we can write here, and it says the measure of the exterior angle of a regular polygon is 360 divided by n, and that is totally worth putting inside a red box. All right, go ahead and pause the video and do our last problem. You should have sped right through that problem. It says, what is the measure of an exterior angle of a regular nonagon? So you see that word regular and you know it is special. So we know that nonagon, n is 9, 360 divided by 9 is 40 degrees. Now I want you to think about this for a minute. That makes sense, right? What was our octagon? Our octagon was 45 degrees. The more sides we add, the bigger the interior angles, the smaller the exterior angles. So let's take a look, and I'm just going to draw in a partial figure here. No special anything on. I'm not going to try to draw a nonagon. But up above, we found the measures. If this is a nonagon, we found the measures of the interior angles of a nonagon. What was that? It was 140 degrees. Right? So if I draw in my exterior angle here, what's my exterior angle have to measure? This we know is a linear pair. So this has to be 40 degrees. Because this whole thing is 180, this little piece over here is 140, so the other one has to be 40. So this should make perfect sense. All right, that was fun. Polygons and their angle theorems. I really think you're going to do well on this homework. These are enjoyable problems.